Okay, let me write down the theorem for second order derivative test. This is most widely used for maxima minima type of problems. Theorem. F of c is a maximum value of the function f if f dash of c is equal to 0 and f double dash of c is less than 0. When we write a statement like this, f is differentiable 2 times, etc. Everything is there. So maybe this statement is not as per our all earlier statements of the theorem. Let A be the subset of R, let F be defined from A to R. Everything is there. I mean, okay. So I give you few minutes to try you write this proof independently, else we will proof. We have seen, we have observed using x square, x cube, x fourth yesterday that this test works, and if second derivative if evaluated at c possess negative value, then it is a local maximum provided f dash of c is equal to 0. Let us write the proof. F double dash of c is less than 0 implies there exists delta greater than 0 such that for every x belonging to c minus delta to c plus delta, f double dash of c is less than 0. Correct? Implies f dash of x is strictly decreasing function on c minus delta c plus delta. As f dash of c is equal to 0 for every x belonging to c minus delta to c, we have f dash of x greater than 0. And for every x belonging to c to c plus delta, we have f dash of x less than 0. Is that correct? Hence, by first derivative test, f of c is local maximum. I think these are the two prerequisite conditions of first derivative test. So we can TKP this and write it. That is good idea. Hence, by first derivative test, f of c is local maximum. This is very interesting and this is very simple. You just visualize what is happening to those particular functions. F of x, what is happening? F dash of x is yet another function. Find out what is happening to that, and f double dash of x is yet another function. Find out what is happening. So if f double dash of x vicinity of c is always less than 0, that means it is decreasing function. At f dash of c, if it is 0, then to the left of c it must be positive, to the right of c it must be negative. And then if you observe f, then slope of tangent to the left is positive, slope of tangent is negative. Therefore, at c it must be maximum. Okay, so let us complete our notes by writing similarly. F of c is minimum value of the function f if f dash of c is equal to 0 and f double dash of c is greater than 0. Okay, so now the question comes is that if f double dash of c is also 0, then we will say you go and look f triple dash, third derivative at c. Suppose that is also 0. Then we will say look at fourth derivative. Suppose that is also 0. Then we will say look at fifth derivative and so on. Therefore, the next maximum minimum test that we will have is nth derivative test.
Excuse me, sir.
Yes.
Sir, in the proof, sir, what is the meaning or the significance of the first step?
What is the significance of?
Like f double dash of c is less than 0 is already given, right?
Yes. So what is the implication of that? That is what we are finding out. Using this condition, f double dash of c is less than 0 implies in the delta neighborhood of c, the function is less than 0 implies f dash is strictly increasing. F dash of x in this interval is strictly increasing. That is the implication. Okay, for every x, it should be x here, not c. For every x, f double dash is less than 0. Okay, because if I write f of c, then this and this statement is same. The meaning of this statement is in the delta neighborhood of c, it is less than 0. So this should be x and not c. Okay, I think that will remove your confusion because for every x we are writing, hence we have to write x here. Is it okay, Harshita? Understood or not? No response, that means understood. Theorem. Nth derivative test. let I be subset of R. Let f be defined from I to R. If one C belonging to I is an interior point, to f n minus 1th derivative exists and is continuous in the neighborhood of C. Third, nth derivative exists at x is equal to C. Fourth, f1 evaluated at C is equal to f2 evaluated at C is equal to f3 evaluated at C is equal to dot 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 is equal to f n minus 1 evaluated at C is equal to 0. Condition number 5. Nth derivative if evaluated at C, if it is greater than 0. And condition number 6. A, if n is even, then 7a, f has local minimum at x is equal to C. Condition number 2, 6b, if n is odd, then 7b, f has point of inflection at x is equal to C. So maybe this we have to write down the definition of what do we mean by point of inflection. So you leave this point at this stage, we will write it, but then because we have written the theorem now, you just start thinking how should the proof of this theorem be? How should we write the proof of this theorem be? That is one. And second, if we could complete the proof of this theorem, then I think if n is even, f has local minimum. This is what is our second derivative test. So it's a special case, right? F dash of C is equal to 0. Then if f second derivative of C is greater than 0, then it is a local minimum. So first part of this nth derivative test, if we put n is equal to e1 is equal to 2, then it is second order derivative test which we have already proved. So check whether you can complete this proof, and it is something similar to just now. Give you sufficient time. As it is given, that f minus 1 exists and is continuous. Near C, there exists delta greater than 0 such that for every x belonging to deleted delta neighborhood of C, that is C minus delta to C plus delta excluding delta, fn minus 1 exists. That is what is this statement. I am rewriting it. So this is the prerequisite condition for our Taylor's theorem. Therefore, applying Taylor's theorem, to interval uh, whose endpoints are C and X of order n minus 1. Taylor's theorem of order n minus 1. If we apply, where now there are actually two cases. Here you have C. Case 1, you have to consider X to the left of C. Case 2, you have to consider X to the right of C. Okay, these are the two cases which we have in mind. So keep it inside bracket. Applying Taylor's theorem, what we have is f of x is equal to base point f of C plus first derivative upon 1 factorial into x minus c raised to 1 plus second derivative evaluated at c upon 2 factorial into x minus c raised to 2 plus dot 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 plus. Now applying it of n minus 1th order, that means my last term here is f n minus 2 evaluated at c upon n minus 2 factorial into x minus c raised to n minus 2, and then I will have that remainder term which is a correction, f n minus 1 evaluated at d divided by n minus 1 factorial into x minus c raised to n minus 1. This is our statement of Taylor's theorem for order n minus 1. The last term is your correction. Okay. Now, it is given that all these guys are zeros from up to all these people. So, given f1 of c equals f2 of c equals f n minus 2 of c, that is what everything is given to be equal to 0, reduces this particular thing to f of x is equal to f of c plus f n minus 1 evaluated at d upon n minus 1 factorial into x minus c बराबर है raised to n minus 1. So this is what we have got now, and we have exhausted the condition that all of them are 0. Okay, so now here what do we say is we have to consider these two cases. Suppose case 1 and n is even. नीट लक्ष द्या. Let n be even. Case 1. Case 1 is x is to the left of c. So if x is to the left of c, x minus c is less than 0. बरोबर है? If x is to the left of c, x minus c is less than 0. Implies x minus c raised to n minus 1, where n is even, so this is odd, is also less than 0. So this quantity is less than 0. This is negative quantity. This quantity is factorial, it is positive. Okay, so therefore now slope of the curve at x is equal to c. Now what we are supposed to use? What is the other condition that is given to us? Other condition that is given to us is about Fn. Fn at c is greater than 0. So this is fifth condition. Fn of c is greater than 0. Fn, let me write it in green. Fn at c is greater than 0 implies Fn minus 1 of x is what? Increasing or decreasing? Slope is positive, nth derivative near c. So Fn minus 1 at x is increasing function. In c minus delta to c plus delta. Okay, so our case, which is the case which is going on? C minus delta to c. Okay, this implies f n minus 1 of x is less than 0 for every x belonging to c minus delta to c. Now here I think where we have taken that d, we should write that d is between c and x. Now if case 1 it is case 1, where is d? X is less than d, x is less than d is less than c. Case 2, c is less than d is less than x. Okay, this is important. That is what is this point, correction. So now we are dealing with this, and it is fn minus 1 at x is less than 0 for every. Therefore, this implies fn minus 1 evaluated at d is less than 0. Correct? So this is less than 0, this is less than 0. Therefore, this implies f of x minus f of c is greater than 0, implies f of x is greater than f of c. Okay, case 2. I will go through the proof again if you are missing something, but I think it is being done very systematic. Case 2. x minus c is greater than 0. Implies x minus c raised to n minus 1 is greater than 0. Okay. Now I think we can, from here we can directly conclude that f n minus 1 of x is greater than 0 for every x belonging to C plus delta. Implies fn minus 1 evaluated at d is greater than 0. Okay, so both of them are greater than 0. Therefore, again we get f of x minus f of c is greater than 0. Implies f of x is greater than f of c. Maybe we can give them 1 or something like this, 2. So 1 and 2 simultaneously imply f of c is local mean. Okay, so I think for even, if n is even, we have done reasonably good job. This is the complete proof in front of you, and this is the theorem in front of you. Taylor's theorem, applying Taylor's theorem makes our life very easy because everybody is zero in between, therefore we get this relation directly. F of x and f of c to n minus 1th derivative. बोला डाउट है लिहून घ्या विचार करा and then I will give you the definition of point of inflection and then we will see what happens if n is odd. Let n be odd. Case 1, x minus c is less than 0 implies x minus c raised to n minus 1 is greater than 0. बरोबर है? Because if n is odd, n minus 1 is even, and whether positive or negative inside bracket, it will be greater than 0. Then I think this conclusion will continue to remain same. Does not matter whether n is even or odd, it is not dependent on that. Therefore, fn minus 1 at d is less than 0. Note fn minus 1 evaluated at d is less than 0. So, this implies f of x minus f of c is negative multiplied by positive, therefore is less than 0. Implies f of x is less than f of c. Case 2, x minus c greater than 0 implies x minus c raised to n minus 1 is also going to be greater than 0. And then the condition here is, note fn minus 1 evaluated at d is greater than 0 implies both of them are greater than 0. Therefore, f of x minus f of c is greater than 0 implies f of x is greater than f of c. Okay, so I mean f of x is less than f of c in the first case when x is to the left, f of x is greater than f of c when x is to the right. This implies and f dash of c is 0. And f dash of c, note f dash of c is equal to 0 implies what does it imply? It implies point of inflection. Therefore, we are supposed to write down the what do we mean by point of inflection. So here you can complete saying that if f dash of c is 0 and if f of x is less than f of c and f of x is greater than f of c to the left and right intervals of c, then implies that it is a point of inflection. Okay, so it is important I write down what do I mean by point of inflection. Definition. Point of inflection is where function changes the convexity. Convex become concave and concave becomes convex. Something like that. Point of inflection is a point at which concavity of the function changes. Okay, so geometrically, say for example x cube, pi is equal to x cube, something like this. So if we call this as concave down or convex down, this is convex up, and therefore at 0 it is a point of inflection. Okay, so sine curve, chord is below curve, chord is above curve. Therefore, this is point of inflection. The convexity or concavity, whatever you call, the curvature changes. Function is continuous, and if curvature changes at that point, then it is point of inflection. Okay, so let us see what happens at point of inflection, and therefore function, if you observe whatever last step we have written here, okay, last step, say for example y is equal to x cube, where anyway cube means n is 3, n is equal to 3, that is our cube. In that case, f of x c is equal to 0, for example, then f of x is less than f of x, the values of the function are less than c, f of c, to the left interval, values of the function are more than f of c, to the right of interval, that is what is happening, and at c the slope of tangent is 0. That is also what is happening here. Okay, and therefore geometrically this particular point is a point of inflection. Chord below curve, chord above, chord below curve, chord above. Now if the function was something like this, minus x cube, Okay, y is equal to minus x cube. Then exactly similar things would have happened, but the signs would have been different, exactly opposite. And then our given condition also would change. Let us find out what is our nth derivative. y1 is equal to minus 3x square, y2 is equal to minus 6x, and y3 is equal to minus 6. So third derivative n is equal to 3. So yn is less than 0, and when we started writing this theorem we took yn as greater than 0. Why? Fn at c is greater than 0. That is what we took in the beginning. If we start with this is Fn at c is greater than 0. For that we have written this. Of course there will be a parallel theorem for Fn at c is less than 0. So the corresponding example is y is equal to minus x cube, which I have shown just now, and everything will fall in place. Proof. And this is what is your point of inflection. Doing that, I think this is what is the theory of maxima, minima, and point of inflection. Okay, now we will find out if there are any irregularities or if there are any counter examples or something which we need to be careful about. We will do that and then we start solving problems. Right. What is normally taught or what is given in the books also. 50%. Normally what is taught or what is given in the books is f dash of c is equal to 0 implies that c is local maximum if f double dash of c is greater than is less than 0 or local minimum if f double dash of c is greater than 0 or point of inflection. If f double dash of c is equal to 0. This is what is the standard statement everywhere. Now I would like to find out by giving you one counter example what exactly is not correct in this statement. Okay. So let f of x is 3x square upon 8 minus 4x plus 29 by 2 if 2 is less than x is less than 6 and minus 5x square upon 16 plus 17x upon 4 minus 41 upon 4 if 6 is less than equal to x is less than equal to 10. Okay, this is what is the definition of the function. Now find out everything about this function. give you sufficient time. You should come up with complete analysis of what is this function and whether we are staying here or normally said or which is normally true in majority of the cases. Is it true in this case or not? Then what exactly is not true? Study this function in detail, find out everything. Maybe sketch, plot a graph, understand it, and tell me what is the outcome. Thank you. So in this particular example, what are the findings? The findings are as follows. Number one, at x is equal to, first of all, if you substitute value 6 in the first expression and 6 in the second expression, f of 6 happens to be same and hence it is continuous. F of x is continuous over 2 comma 10. Okay, this is polynomial, so of course it is continuous between 2 to 6. This is polynomial, therefore it is continuous between 6 to 10. But at 6, these numbers are so adjusted that both the values are same, therefore it is continuous over 2 comma 10. Now, is it differentiable? So if you find out dy by dx of the first part, dy by df dash of x of the first part and of the second part, किती येतं उत्तर? At 6, 3 by 4 x, नाही काय येतं half, at x is equal to, so this function is anyway differentiable over 2 to 6, this function is anyway differentiable over 6 to 10, and the derivative at x is equal to 6, then you get it equal to half. So that means it is implies differentiable over 2 to 10. Correct? No problem. Now, this is positive leading coefficient. So it is something like this. And then from here, the second curve takes over. It becomes like this. So you have, this is I think 0.6. You have local minimum. At 16 by 3. Hello? Hello? And local maximum at 34 by 5. This is 16 by 3. This is 34 by 5. And to the left of 6, it is convex up, chord above curve. And to the right of 6, it is curve above the chord. So at 6, it is point of inflection. Right? But d2y by dx square at x is equal to 6 does not exist. Because if you find out derivative of the left branch, then the derivative comes out to be d2y by dx square for the first branch, that is 2 less than equal to x less than 6, you get equal to 3 by 4 and you get this as minus 5 by 8 from 6 to 10. And they are not equal, nor both of them are 0, but still we have point of inflection. So that That is what is the discrepancy. That is what is the counter example. It is
ते पॉइंट ऑफ इन्फ्लेक्शन हे आपण कसं डिटरमाइन केलं?
पॉइंट ऑफ इन्फ्लेक्शन आहे हे कसं डिटरमिन होतंय, कारण from 2 to 6 it is scored above curve. This is leading coefficient is positive and it is a quadratic equation, so the curve is going to be like this only. We know that leading coefficient is negative from 6 to 10, it is going to be like this. And otherwise you take any 2 points to the left and find out the chord whether it is above curve or not. You will find that in this branch it is chord above curve, in this branch it is chord below curve. Therefore it is a point of inflection. Physically, graphically it is a point of inflection, but d2y by dx square is not equal to 0. It is continuous and differentiable, right? So if f double dash of c is equal to 0, then point of inflection is true statement, because fine, then this is true. But there could be cases where f double dash of c is not equal to 0 and still we have point of inflection. This is what you have. So this is one of the necessary conditions for being point of inflection, that f double dash of c is equal to 0. But if f double dash of c is not equal to 0, does not mean that there is no point of inflection. That is why this example is important. Let me give you one more example. Have you understood? This is discontinuous. F double dash of x, this jump discontinuity here. They are not same. At 6, left hand derivative, double derivative is 3 by 4 and right derivative is minus 5 by 8. Those tangents do not match. Let me give you one more example. Example 2. Y is equal to minus x cube. Study this. Tell me everything about this. Why is this yet another counter example? I'll give you some time. Okay, y is equal to x cube minus x cube is well behaved. But y is equal to x raised to 1 by 3. That is what I wanted to give inverse of this. This is good because our tangent is horizontal at x is equal to 0. But the moment I take inverse function of this, tangent is going to be vertical. Right? So check. I should have given you this function, not this. Y is equal to minus x cube or y is equal to x cube is like this. So its inverse is going to be like this, and therefore if you draw tangent at x is equal to 0, it is going to be vertical. So what is the first derivative of y is equal to x raised to 1/3, y1 is y dash is equal to x raised to minus 2/3. बरोबर है? And y double dash is equal to minus 2x raised to minus 5 by 3 upon 9, something like that. So this x is in the denominator, and if you put x is equal to 0, undefined. But still, if this is the curve, this is chord above curve, chord below curve. Therefore, there is a point of inflection. So these counter examples are saying that there could be point of inflection otherwise, and f double dash of c need not be equal to 0. Still, you may end up having point of inflection. So these are the important counter examples which will ensure that f double dash of c is equal to 0 is one way to achieve point of inflection, but not always. Okay, so I think we have 35 minutes with us, and we should solve a couple of problems. So we are nearing end of differential calculus. We are nearing end of differential calculus. Write down problem. A length of wire is to be cut. Question 1. In two pieces, such that first part is used to make circle, and second to make square. First part is used to make circle, and second to make square. Find the cut. Find the length from, say, left. Cut so that area is maximum. Total area. Understood? There is a wire of length, say L. You need to cut it at, say, X. I am giving you the setup because the variable is X. Total length is L. First part is made, this X length is used to make circle, and L minus X length is used to make square. Okay. So give us what length X of L we should cut so that we get maximum area. This is the first problem in finding out maximum minimum, and majority of the students make mistake. It is said that where should we cut the wire so that we get maximum area, and they're good, they write the function very well, but unfortunately do not look at the second derivative. Let me create area function. Area of total area is equal to X is the perimeter, therefore काय येणार पहिला एरिया x square upon 4 pi, बरोबर आहे, is the area of first part, and area of second part is what? L square minus 2lx plus x square upon 16. That is L minus x upon 4 bracket square. So this is your area function, and you differentiated it. dA by dx, you found out because you were expecting maximum or minimum, therefore tangent should have slope equal to 0. You equated it to 0 and then solved it to get x is equal to pi L upon pi plus 4. Okay, and you reported this answer, which is not correct. Because if we take second derivative of the area function, we get 1 upon 2 pi plus 1 upon 8, which is greater than 0. So if second derivative is greater than 0, you are supposed to get minimum. So this length which you have found out is minimum. However, geometrically it is very easy. You start, this is your 0 and this is your length L. Okay. If x is equal to 0, that means use complete wire for making square, then the area is L by 4 bracket square. So L square by 60. Suppose that point is here. And the second area of circle is 0. Okay. Then area of square will keep on reducing as you keep on changing the value of x. So if x becomes positive, we are getting little less length for making square. It should be function like this, decreasing function. If you use complete area, complete length for making the circle, the first part is 0 and the circle is L square by 4 pi. Is that right? So L square by 4 pi, 12. So this quantity L square by 4 pi is going to be smaller or bigger?
Bigger.
Bigger, na? L square by 4 pi is going to be bigger, and then this is going to be like this. Okay, and then when you add both of them, you get a new function which is like this. You are adding, and eventually they are going to go and hit here. So this is what you have. This is what you have found, minimum area. That is what your pi L by pi plus 4. And you want maximum area. This is your max. This is your mean. This is your local max. So amongst these two max, you should choose the global max, and hence x is equal to L. Understood? So this is what was your first problem. So you just don't go by the wording, you have to have a geometry in your mind. Moreover, if you would have found out the second derivative, you would have got an alarm saying that, boss, we are finding out minimum, not maximum. And at both the places, this condition is same. If you are finding minimum or maximum, first derivative you are supposed to make it equal to 0 and get those critical points. Okay. Now, critical points. Which are the critical points? How do we find the critical points? One, endpoints. If it is an interval, endpoints are always critical points. You have to pay proper attention towards endpoints. If you would have paid proper attention to the endpoints in this problem, your problem would not go wrong. That is first critical point, end point. Second, where tangent has slope 0, so take first derivative and equate it to 0. First derivative equal to 0. Find out those points. They are the important points for you. Maybe third, value of the function equal to 0. That is yet another important point for you, where you come to know that the graph is crossing x-axis at that point. And fourth thing that you should find out as a critical point is if derivative does not exist. That means tangent is vertical or discontinuous or something like that. So these are the critical points which you should collect the moment you form a function or you get a function. You should figure out what are the important points definitely I would like to study. Otherwise, between the critical points, the function is going to be well behaved. So which are the points where I have to pay more attention? I have to be more sincere with those points. And how do you find those points? This way. In this case, the critical point was this. You use this to find the critical point, and then you ignore the end point. Okay, and that is why it was wrong. So this is the first example that we have solved, and we stop here for today. We will solve many problems in the next lecture, next week. But theory required for solving maximum minimum problems is done. Basically, word problems are always difficult, and if those are related to minimum maximum problems, applications of derivatives, then first thing that you should do is you should find out what is the dependent variable, what is independent variable, and how are they related to each other. So forming the function which is to be maximized or minimized is important. After that, algebraic calculations. The theory is ready for proceeding after you have the first function with you. In word problem, that function readily is not given to you. You have to form that function using your previous knowledge. Okay, so we will solve many problems in coming lectures so that you are good at applications. Then we will draw many graphs so that you come to know very quickly what is the nature of the function. Okay, so I stop recording.